Where does your phone really come from? Or your car, your house, even the paint on your walls? It's a question we don't often stop to think about, but the answer, it takes us deep underground into a world most of us never really see. So today we're doing a deep dive into the, frankly, fascinating and complex world of mining methods and the raw materials that basically underpin, well, everything. We've been digging into some really detailed research, specifically Chapter 6 of Mining and the Environment by Dr. Karl-Heinz Spitz and John Trudinger.
And our mission today really is to unpack what's essential here. We want to reveal some maybe surprising facts, connect the dots so you can really grasp the why behind these huge operations and understand their impact, which is often profound, sometimes invisible on our world. It's so much more than just rocks and dirt. It's literally the foundation of everything around us.
Okay, let's unpack that then. When you think mining, what's the first thing that, pops into your head? For a lot of people, myself included, it's probably those big images like gold rushes, maybe sparkly diamonds or huge coal mines. But I was genuinely surprised reading this, just how broad the definition actually is. It goes way beyond those familiar pictures.
Yeah, you've hit on a really key point there. What's fascinating is that mining isn't just about pulling metals or fossil fuels out of the ground. It actually covers this huge range of stuff. Dimension stone, for example, which is basically just rock cut to specific shapes and sizes for building. Or think about everyday sand and gravel, vital building blocks. Then you've got clays, ceramics, chemical deposits, even fertilizer minerals, which are crucial for growing our food. And the specific method they use, that often depends completely on the material itself and how it occurs naturally in the earth.
Right. And I found one statistic in the research just mind-boggling. Did you know that the actual monetary value of non-metallic minerals mined worldwide actually far exceeds the value of metals? That feels completely backwards. How does that work?
It does sound counterintuitive, doesn't it? But think about the sheer volume. Take dimension stone again. We're talking about iconic stuff like Carrara marble from Tuscany. People have been quarrying this for over 2,000 years. Michelangelo used it. And incredibly, they still quarry 1 million tons every year.
1 million tons, wow.
Yeah, even as the really pure white stuff gets rarer. Or think about something that seems really mundane, like sand and gravel. They're fundamental for pretty much all construction. And interestingly, where you find them, their closeness to building sites is often more important than their exact chemical makeup. It can even spark political issues, like Singapore importing loads from Indonesia.
Huh. So connecting that to our everyday lives then, it means the concrete in our building foundations, the asphalt on the roads, even the glass in our windows, that stuff mostly comes from this massive but overlooked industrial minerals sector. It's literally the groundwork for everything.
Exactly. And then, of course, you have the metallic ores. These are probably what people think of more often with mining, beyond the usual suspects like iron or copper. The research highlights the light metals: aluminium, magnesium, beryllium, titanium. Super light, but incredibly strong. Aluminium, for example, it's the most common metal in the Earth's crust. But making it from its ore, bauxite, takes a huge amount of energy.
Right.
But despite that, it's critical for aircraft, cars, even the drink cans in your fridge. And titanium, named after the Greek Titans, which is cool, it has this amazing strength-to-weight ratio, resists corrosion. It's used in everything from paint pigments to medical prosthetics, even rockets.
Okay, and beyond those, the research also talks about this group called rare earth metals being absolutely vital. I have to admit, I don't know much about them. The name sounds important, but also maybe a bit misleading. What are they, and why do we need them so much if they aren't actually rare?
That's a great question because, yeah, the name is misleading. They're a group of about 30 elements, often down at the bottom of the periodic table. And like you said, they're not really rare geologically, nor are they Earth's. But what makes them critical are their unique magnetic and luminescent properties. They are absolutely essential for modern tech. Think navigation systems, radar, night vision goggles, and maybe most importantly, the batteries and mobile phones we all rely on every single day. Elements like cerium, lanthanum, neodymium, they're literally inside the device you might be holding right now, making it work.
Wow. Okay. And the supply chain for these is quite concentrated, isn't it?
Very much so. Back in 2017, China accounted for something like over 80% of the world's supply of rare earths and over 2/3 of the global demand. So that highlights not just their industrial importance, their strategic value globally. Makes them pretty interesting geopolitically.
Absolutely. And okay, we can't talk mining without mentioning gold, even if most gold today doesn't come from giant nuggets. That historical gold fever is still a real thing, right? I loved reading about Bernard Otto Holterman back in 1872, Australia. Found this incredible 630-pound mass of almost solid gold.
Yeah,
It's not a nugget. That's like a gold boulder.
It really captures the imagination, doesn't it? The dream of striking it rich. But yeah, today, the real money, the real economics are in these serious, large-scale operations. They're meticulously extracting just a few grams of gold from tons of rock. It's a very different game from the lone prospector.
Right, a different world. And finally, just quickly, mercury. It's unique, the only liquid metal at room temperature. And traditionally, it was super important for getting gold out using this process called amalgamation. But it's also incredibly toxic, which, as we'll see, causes huge problems.
A double-edged sword, for sure.
We've talked about these massive operations, the open pits, the ones we might picture. But are there other ways, methods that are less about moving mountains and more subtle, maybe even invisible?
Oh, absolutely. While open pit and strip mining are how most minerals and coal get extracted globally, think about the Canadian oil sands. Takes 2 tons of sand for 1 barrel of oil.
Wow.
There's a whole spectrum. Underground mining, for instance, is much less visible on the surface. It's more complex, more cost per ton, sure. But the aim is to target the ore body directly. You remove much less waste rock, and the surface disturbance is significantly less, much smaller footprint.
Okay. And then the research brings up something called heap leaching, which honestly sounds almost like science fiction. You just pour liquid over rocks. How does that work?
It does sound a bit strange, but it's actually a really common and established process, especially for lower grade ores where other methods might not pay off. Think of it like a giant coffee filter for rocks. You crush the ore, pile it up in these big heaps on prepared pads, often lined pads, then you slowly trickle a solvent over it. For gold and silver, it's usually a very weak cyanide solution, and as it percolates down, it dissolves the target metals.
So you're basically just washing the metal out. Okay, that sounds efficient for those low-grade ores, but cyanide, that immediately raises environmental questions, right?
Absolutely, that's the critical point. The most important part of designing these systems is the liners. Robust liners for the pads the heaps sit on and for the ponds that collect the solution. They have to prevent any leakage, any groundwater contamination. So yes, there are risks, like with any big industrial process, but they use careful water balance calculations, they size the ponds correctly, they use strong, properly installed liners to minimize those risks, and actually cleaning up afterwards, rehabilitating the spent ore from heap leaching is considered relatively straightforward. The leftover rock is pretty stable.
Okay, and then even more invisible. In situ leaching and solution mining, you mentioned not even having to dig the ore up. Is that really how it works?
Precisely. In situ leaching means dissolving the minerals right there in the ground, without removing the ore at all. It's mainly used commercially for uranium and sometimes for copper. You pump a solution down through injection wells into the ore body, then you pump it back out through other wells and it brings the dissolved minerals with it. So yeah, you literally don't dig up the ore. On the surface, it looks incredibly clean. Minimal disturbance.
That sounds amazing from an environmental perspective. Almost too good to be true. Are there hidden downsides when you're pumping stuff underground?
You're right to ask. While the surface impact is tiny, the challenge is controlling that solution underground. It's harder than in a contained, lined heap leach system. Making absolutely sure those process solutions don't migrate away from the target area is the main concern. It needs really careful groundwater management. Solution mining, which is similar, has been used for decades for things like potash, soluble salts buried deep down. You just inject water, dissolve the salt, and pump it out. That's generally pretty benign.
And looking way out to the ultimate frontier, perhaps. Seabed mining. Is that actually happening yet, or is it still mostly sci-fi?
Deep sea mining, or DSM mining minerals from seabeds deeper than, say, 500 meters, it doesn't exist commercially yet, not on a large scale. But companies are actively exploring. Nautilus minerals, for example, off Papua New Guinea, looking for gold and copper at depths of 1,000, 1,500 meters. It's deep.
Right.
Most of these potential deposits are way out in international waters, beyond national economic zones, so they're governed by the International Seabed Authority under the UN Law of the Sea. But the challenges are just immense. Really distant locations, extreme pressure, extreme temperatures, and maybe the biggest hurdle. We just don't know much about those deep sea environments, what the impact would be.
Right. So it's very much early days.
Very early days. Whether it becomes commercially viable or even environmentally acceptable, that remains to be seen.
Okay, so we've covered these huge industrial operations, massive machines, complex engineering, but there's this whole other side to the story, isn't there? A totally different approach that actually accounts for a massive chunk of global mining employment. Artisanal mining. Small scale, often just manual digging, done by individuals, families, small groups. sometimes called small-scale mining, sometimes, if it's on land someone else owns, illegal mining.
Yeah, and it's a really important distinction. It's a traditional way of life for millions of people globally, practices going back centuries. It provides a vital livelihood, but it also carries this huge potential for really severe environmental damage. We can broadly separate it into two types: these chaotic, often destructive gold rushes, and then the more structured, traditional small-scale mining.
Right, the gold, that sounds like something straight out of the history books or an old movie. Does it really still happen like that today?
It follows a remarkably similar pattern, whether it was California in the 1840s or modern rushes in Brazil or parts of Asia or Africa. It kicks off with a discovery, often easy to get stuff like gold in riverbeds, placer deposits. News spreads like wildfire, and suddenly you get thousands of people flooding into the area, all sorts of backgrounds, desperate people, opportunists, sometimes criminals. The first techniques are simple, maybe just panning, but the whole situation often leads to, well, lawlessness, incredibly unsafe working conditions because there's no oversight, poor sanitation, and crucially, very few of the actual miners strike it rich. It's often the moneylenders, the traders, the people supplying equipment who actually make the most money out of the situation.
I can easily imagine that leads to serious conflict, especially if these rushes happen on land that, say, a big company already has the legal rights to mine.
Oh, absolutely. Clashes between companies with legal mining licenses or tenements and these sort of informal or illegal miners are really common. But what's interesting, and the research points this out, is that companies are often quite reluctant to just call in the government or police to forcibly remove them.
Why is that?
A big reason is the bad publicity. It's very easy for the company to be painted as the greedy corporation, crushing the little guy, destroying traditional livelihoods. NGOs can be quick to jump on these stories, sometimes with, let's say, biased accounts or exaggerations, so it becomes this big PR headache for the company, even if they legally own the rights.
Right. And environmentally, particularly with mercury use in these gold rushes,
Right.
the impact is just devastating. That's a really critical point.
It's a profound, just tragic problem. These artisanal miners often rely on mercury amalgamation to get the fine gold out. Because it's cheap, it's simple, you don't need much equipment, but environmentally it's catastrophic. The mercury gets vaporized when they heat the amalgam, often done indoors, exposing the workers and their families to toxic fumes. And then the mercury-laden waste, the tailings, just gets dumped straight into rivers or onto the land. It contaminates everything: soil, water, fish.
So what are the actual human consequences when people are exposed to this mercury? It sounds horrific.
The health effects are severe and often insidious. You mentioned Minamata disease in Japan, caused by organic methylmercury that killed over 1,000 people. Now, while direct links like Minamata haven't been fully proven from artisanal mining, even the inorganic mercury they typically use is really bad news. It damages the central nervous system, the endocrine system, your mouth, gums, teeth. High long-term exposure leads to serious brain damage, Mad Hatter's disease, as it was famously called, and eventually it can kill you. And the awful thing is, the symptoms can be subtle at first, taking years to show up, especially in remote areas with poor health care where it just goes unnoticed.
Is there one specific example that really drives home the sheer scale of this mercury pollution problem?
There is, unfortunately. The research highlights the pollution from artisanal gold mining around Mount Muro in Kalimantan, Indonesia. It's considered globally significant. In 2015, they estimated that 90 tons of mercury were being released every year just from that one area.
90 tons.
Yeah. That's about 7% of the total global mercury emissions for the year, just from that one spot. Local NGOs have even called the Burrito River there the Chernobyl of mercury pollution. It's that bad.
That's staggering. And beyond the terrible health and environmental toll, there are huge social costs too, right, with these chaotic rushes.
Huge. These rushes can completely tear apart traditional societies, especially when you get large numbers of outsiders pouring into areas where maybe vulnerable indigenous groups live. Massive population pressure, spikes in crime, people lose access to their traditional resources, their farming land, prostitution, drug use, HIV/AIDS often become rampant. And often, the temporary economic boost for a few just doesn't come close to justifying these deep, long-lasting social and environmental costs for the whole community.
It really sounds like a nightmare scenario, which makes the contrast with the traditional small-scale mining you mentioned earlier even more striking. How is that different? Can it offer any hope?
It's a powerful contrast, absolutely. Because traditional small-scale mining, like the Cancanay community practices in the Philippines, and they've been doing it for over 800 years, it can be remarkably sustainable.
800 years.
Yeah, it's characterized by things like strong community cooperation, a really skilled workforce who know the ground, pretty good recovery rates for the minerals, and stability even when prices fluctuate. Their underground mines cause minimal disturbance on the surface. They're much safer, too, because these miners have generations of knowledge about ground stability. And crucially, they don't use mercury. They achieve over 80% gold recovery using clever physical separation techniques. They're meticulous about conserving and reusing water. It just shows what's possible when communities have that deep connection to their land and their practices. It shows there is a sustainable way, even for small-scale extraction.
Okay, so bringing this all together, what does this mean for you, the listener? Going about your daily life in a world that depends so much on these often hidden industries?
I think it means realizing that this world of mining, which might seem distant, is actually incredibly diverse. You've got everything from these vast, high-tech industrial operations right down to small, resilient family groups. And it really is the essential backbone of our modern lives. It provides the raw materials for pretty much everything we use and touch, from the tiniest microchip to the biggest building.
Oh, yeah. But the methods they use, and therefore the impacts, environmental, social, health, they vary enormously, don't they? You go from the controlled, almost invisible solution mining all the way to those chaotic, dangerous, and polluting gold rushes. It's this whole spectrum: innovation, tradition, progress, and definite peril.
Exactly. And ultimately, I think it raises a really important question for all of us. How do we keep meeting the demands, the growing demands of billions of people for these essential materials, while making sure the way we get them is both environmentally sound and socially responsible? How do we learn from the successes, like those sustainable traditional practices, and really tackle the huge challenges posed by the destructive methods?
It's a huge question. Maybe the next time you pick up your mobile phone, or drive down a paved road, or even just admire a piece of marble, maybe you'll have a bit more appreciation for the incredibly complex journey those materials took to get to you. And the profound human stories and environmental stories that are often hidden just beneath the surface.